Okay, good morning. Yeah, I actually forgot to bring the sign-up sheet. I just asked one student to go back and pick it up. Okay, but we were still signing all the attendance just every day. I just forgot to bring that. Okay, so last time we discussed. Okay, let's go down. Last time we discussed about network, some basic properties of the network. Okay. Today we are going to go down a little more to see the detailed measure, the centrality measure. Okay. Probably before that, I should also just mention a little. Okay. Remember, we have the sign-up sheet for you to sign up for 10 minutes per presentation. Okay. We did have quite a few students sign up. I still wish to have more students sign up. Okay. Some people on Piazza just asked whether you sign up, you still have to do survey. Okay. These sign up replace your credit for your survey. But if you still want to join other groups, other group members to form a research group and to do a survey, you're welcome. What I said is the survey score and the presentation score will pick up the higher one. Okay, so that's the major advantage. Of course, if you do not want to do a survey, you do not have to do a survey. The presentation is different from the group survey. It's presentation usually only read 1 or 2 papers. For 10 minutes, you only have time to present 1 or 2 papers. You don't have time to present like 20 papers. But for survey, likely you have to read many papers, digest them, and summarize them. I expect you have to read at least 10 to 20 papers to do a good survey. Okay. But since presentation, you need to very carefully digest, then you present in a nice way. It does take some effort. That's why we give you the whole credit of survey. But we do not encourage you to do the group presentation because only 10 minutes, if you get 3 or 4 people standing there, only one person say 2 or 3 minutes, it does not really work that well. Okay. Plus, it's only 1 or 2 papers. So we hope if your group really wants to do a presentation, you say everybody wants to present, then you split into 2 or 3 presentations. Everybody take 10 minutes. That may work. That may work out as well. Okay, so that's the format. Any questions regarding this? Hopefully that clear up the questions on Piazza. Okay. Then we are going to continue our discussion, but also I probably should say is you go down to several pages I should point out. One is recommended research projects working together with the data mining group. You probably see there are quite a few projects listed there already. But some, like the first one, is already fill up very quickly. So you try to make sure you read those carefully, you communicate with these students or postdoc, but you need to be prepared. If you got an interview, they say finally he or she doesn't want to take you. That's fine. You find your own project because sometimes they want to pick up the students who have similar background or enough interest. They want to interview people to make a pick. Okay, but you should start early because later some already got to fill up, so you will lose the chance. Another one I should mention is the resource page. Okay, if you click our home page, CS512 home page, this one actually obviously is not the CS512. If you click our home page, there's one called resources where it is. Yeah. The resource page also is very useful because when you read even now the class notes, I will give you the links for example, you click this button, you go to Professor Mohammed Zaki at RPI, his book page. You can download his whole data mining book for free. I believe it because I downloaded many days ago, 2 years ago. I think it's still open. You can click it. You can buy the book. But we actually, our chapter somehow only relate to his chapter 4, graph data. Okay, so you can get this. You can download it. This like a, additional reading. Another one is you can download Christos Falousa's book, Graph Mining. Okay, that's his book. If you go to UIUC site, you download it, probably it's for free. If you just go to any page you download it, they probably will charge you $20 or ask you first pay to download it. Because UIC library actually linked to this one. You go to UIC, you go to the engineering library, you go down this page, you download it, it's free. Okay. But it's a very good book. It contains lots of stuff we discuss and beyond. Okay. So those are good sources for you to study the course materials. Okay. So hopefully you will be able to use it in a very smart way. Okay. Now we come down to our page. Okay, I think this picture everybody knows where it is. This is Pisa, Italy, the Leaning Tower of Pisa. Okay, that's where several hundred years ago Galileo, put two wooden and steel ball or iron ball, it dropped down to the ground at the same time. So that's the most scientific history-wise, this is probably the most famous architect. But it's still, now you still can climb up. I actually will in some later picture, I will show you when we climb up this leaning tower, the tower is really leaning. You stand there, it's not a straight fall, 90 degrees. You actually can see the tower. But every time they only allow a very limited number of people to get on because they were afraid to get too many people. The tower really collapsed. They actually closed the tower for, I think, at least 10 years. I went there several times in like a year, early 2000 or 1999. I could not climb it because it was sealed. But I went down there in 2008, I could climb up. They reopened it. Okay. This is the church just nearby this tower. Okay, now let's look at the second issue we are discussing is centrality analysis in networks. Okay. In a big network, you always want to measure the nodes. For example, in a social network, you want to measure particular nodes, like Barack Obama, how centered or how popular he could be. You can see a movie star or yourself. You want to measure it. One important measure is centrality measure. That means this node, how centered it is in the whole network. Okay? So that one we call centrality measure. This centrality measure is critical for example, Google's page rank. Okay? Because you want to automatically rank this page upon your search keyword. Okay? For example, you search UIUC. You want really UIUC homepage somehow right on the very top. Then you don't have to dig down into many, many pages to try to find the UIUC homepage. So it's critically important. You don't want it to do it by human. You want to do it by computation. Okay? That's exactly why people are interested in centrality measure. Okay? Centrality measure, actually, there are many, many definitions or measure the concrete formulas on centrality. The first one, which is very simple but popular use, called degree centrality. Degree centrality means how many nodes, how many links this one carries. Of course, you may say the links contains in-link and out-link. Okay? It means For example, you see Barack Obama, you may see there are many, many links point to Obama. That's in link. But if you just calculate the in link, you may say Obama is pretty center. It's a very high degree. So that's degree centrality simply says you link to more edges, your centrality is higher. Okay? So that's a very simple notion. The second centrality measure called eccentricity centrality. Remember last time we said whether your node is in the center of the graph or in the peripheral, at the edge, at the outside of the graph. So this actually is eccentricity, centrality. Eccentricity, essentially, the definition is E. Okay, this E definition actually said that VI is eccentricity. Actually, the center node means it's closer to the center of the graph. So that means it equals to the radius. But if you get quite far away from the center, okay, so your eccentricity is actually equal to the diameter. Okay. Remember, we actually, if you forgot it, I probably just bring the graph back. You probably can see it. Where's the graph? Yeah, I think that's eccentricity. So it simply says A is the center because A linked to everyone. It's only one you can reach it. Okay, so that's the center. But like F could be out at the peripheral. The reason is F actually because the whole graph, the diameter is 2. So, but F is 2. You can see F, B, D, H. Their eccentricity is 2. It simply says their degree or they are outside the one.
Sorry that I didn't find the sheet, and also I didn't save it back, so I print another one.
Oh, okay. That's fine. Okay, that's good. Yeah, he could not find my. That's the one. I probably just pass it because I will finally put on the web as well. Okay. If you really want to check the web page, I can give you the web address. You can check whether the registry is right or wrong. But usually when I bring it, you probably can see the previous one. If you are here, I did not put any mark. If you are missing, your signature is missing, I put some mark there. Okay. There's one student who could not get a visa, who could not come. I put a different one. I put a light bulb. Simply says you have a good reason to miss. I won't give you a penalty. Okay. But for others, if you're really sick, for example, you really have a doctor's proof you are sick, you got flu, you cannot come, I'll put a light bulb. Simply says this is a good excuse. I will not count as penalty. But if you have no reason you do not come, I do count you miss one class. Okay. So that's eccentricity. Now we come down to this one. This eccentricity centrality, basically you want to say if you are far away from the center, it's closer to the diameter of the graph. So your eccentricity is high, your centrality is low, right? That means you're pretty outsider. So then your centrality will be lower. So the definition is very natural, is 1 over eccentricity. Simply say your eccentricity is pretty high. That means you are very outsider. So then your centrality is low. You are right in the insider. Okay, you're right in the center. Your eccentricity C will be higher because your eccentricity is low. Okay, so this actually, what's the use of this? Just thinking about, like you want to locate like a fire engine, firehouse, or emergency, rescue somewhere, right in the center because you want to reach everywhere closer. But if your fire station is sort of right at the edge of the city, anywhere you get a fire, you have to drive a long way, which may take may take time. So this eccentricity actually has its usefulness. Another one is a closeness centrality. Closeness centrality, of course, you can define the closeness. Most people define the closeness in the graph. We call shortest path length. That means you take the shortest path, you can reach there. The difference is you actually want to look at the close centrality is you can see there's a sigma here. Sigma means you add from this node, for example, suppose you want to set up a shopping center or a post office or something. Suppose you want to calculate everybody, not only one person, takes shorter distance. Everybody adding together, they take shortest distance. Okay, so you think that's likely the shopping center may want to do that. You want to locate the place everybody accessing, on average, will be, shortest distance. In that sense, what you do is you take this node, you check all the other nodes, okay, the total distance to you. Then you sum them up, okay. Then you use 1 over this, you get the closeness centrality. You probably can see these two are still different, okay. The eccentricity means you see whether you are outside of these. You look at individuals. You don't care all the others adding together, okay. But the closeness, actually, you will see all the other things reaching you. You get a total once. Then you see the total distance is minimized, okay. This is very useful for example, a delivery center, okay. If you think about UPS, they want to set up a center in their city. They usually want to set up the center. Their total distance is somehow minimized, okay. So that's a closeness centrality, because you want to reach to many, many customers, right? Then there is another centrality called betweenness centrality. Betweenness means actually you will think which node is a critical one. Everybody will go through you. Okay, that's a betweenness. This is very useful for you design like the internet, the real network. They have a backbone. They have several nodes which everybody will go through. Okay, so if you think about this betweenness centrality, it really somehow determine your network topology, right? If you get into the center, everybody go somewhere will go through you. Like when you fly, I think the O'Hare Airport is one of the bottleneck. Like if you fly from here, you first fly to O'Hare, then you fly to other places. So then you have to go through this node. That's why, like if you think about the shortest path, it will go through a particular node, and that node will play an important role in the computation. Okay, so this is betweenness centrality. But we actually most interested in another one called eigenvector centrality. Okay. This centrality actually was somehow developed in PageRank or in HITS. Okay. They all consider this centrality is a very important one. What is eigenvector centrality? Okay. Originally, you would think when we do like the facility allocation or everything, you think every customer is equal. Somehow you put them same weight. But on the web, you think about the page, web page, you want to find something. Not everyone is equal. Okay, that's a very important concept. That means you would think, some nodes probably play more roles, may have more scores. Even you think in a political forum, you probably see like Obama or some, like presidential candidates. You see they mention so often, so the attention is focused on those nodes. Those become unequal. They have a higher score. Actually, for PageRank, when they first developed, they were thinking about it, how to try to find which node will be ranked higher. Because when you list, you give me a keyword, you list a bunch of nodes, automatically some nodes should be ranked higher. But how do you compute it? You get this one, they rank higher, you put them in the front. How can you do that? Actually, finally, people found this eigenvector centrality would be very useful. Okay. What is eigenvector centrality? Basically, you were thinking everything was interconnected, but the one who put a link on you actually somehow endorse you. Okay, if you think about this, you put a link to Obama, you somehow endorse Obama. You don't endorse anybody, anybody in the world or everybody in the world. You only endorse someone, right? So that's the one you were thinking the links will pass some important information. Okay, let's look at this eigenvector centrality in a little more detail. The eigenvector centrality, sometimes you read the newspaper, they don't bring this more mathematical term there. They call prestige of the node or rank of the node. That's exactly the page rank. They don't call eigenvector, they call page rank, right? It's much more accessible to most people. Okay. Then the general philosophy is this. If you think web is a directed graph, directed means you put a link to somebody else, not necessarily somebody else will link to you. Okay, you just think about this. Suppose you put a link to Google, or you put a link to Microsoft, homepage. That may facilitate you to search or something, but they may not put any link back to you. Okay, this is a single direction, right? You link to them. Then we will look at how to compute this eigenvector centrality. Simply says somebody linked to somebody. If this node is no-namer, okay, it's somebody just like a fans, okay, they link to this page. Of course, that link, every link may count as one. But if you get some very important people, okay, for example, suppose Hillary Clinton put a link to Obama, or John Kerry put a link to Obama. It's different from you put the link to Obama, because you just probably as a fan or somebody, you just put it there. But if this one is, the Secretary of Defense, Secretary of State, they put link down to Obama, that means something different. Okay? So they need to calculate, say, the important node endorse you, this endorsement is more important than the no-namer endorse you. Okay? But how do you know this node is important? How do you know this node, for example, this is Hillary Clinton. How do you know Hillary Clinton is important? Just because many other nodes link to Hillary Clinton, right? You think about this. That means you just based on those links, you sort of figure out the information, which node is important, by doing this computation. But at the very beginning, web as a graph, everybody was equal in the sense you did not know who is important, which node in the graph is important. At the very beginning, you can assign the weight everybody is one. But then you can start the computation by how many nodes point to this one, you increase the weight. Once this one increases the weight, this one point to the others, and the others actually get more endorsement than the single normal, weight one node. And this needs to be repeatedly computed, because at the very beginning, you assume everything is one. You did not know this is Hillary. Okay? And then this node point to Obama, you treat it the same as you point to Obama. Right? But after a while, after certain iteration, Hillary is important, and if she points to Obama, that probably is more important. So that means only after certain iteration, when everybody's rank or weight or prestige got stabilized, that computation become more precise, right? So that's exactly the eigenvector computation in the matrix. If you think the big graph is a big matrix, you need iterative computation until it gets stabilized. Okay? That's the computation of eigenvalue, eigenvector as well, right? So that's the reason you can see how this eigenvector centrality is defined, or you can say it's computed. That means the general philosophy is the more nodes point to a node, then this node, the prestige will be higher. Okay. And the more prestige of this node, then it point to another node, then this one's prestige will also become higher, right? That's just these two. It's easy, to reason. Then you can write down as a single step. You can write down like this. Okay, that means you want to compute V's prestige. Then you can see this is U. The U actually point to V. You can add them together. Add all things together, you actually can compute this one's prestige, right? If you write this one in the transpose matrix, you write down like this. But remember, this is one step like this. You actually need to put them in a loop. Okay, finally get a whole matrix updated until it gets stable. Okay, so that means if you write a form, this is vector form, but you want to calculate iteratively. So every iteration, this A's transpose will get one more round. So the kth iteration, this will be to the power of k, right? So, of course, once you get a stabilized, you really get an eigenvector. That's one. Once you get stabilized, you get the eigenvalue. That means you computed the eigenvector centrality. Yes? Can you speak a little louder? I could not catch you. You speak again? The matrix A is adjacency matrix. Okay, that's originally when we. The question is, what is this A? A actually is your adjacency matrix, right? You remember when we define the graph, we always take A as the original. You can see. If you get a computation, this A actually is an adjacency matrix, which one is adjacent to which. When you do the computation, you can see you do the transpose, then you can compute them, again. You actually compute the eigenvector. Okay. Yes? This A transpose to the power k, because you can see this is uv, then you get another vu. Actually, if you compute this vector, you can see this vector. This is the original node. This vector. This is the case one, and if you this adjacency matrix, originally UV, once you transpose it in, becomes VU. And when you compute, this so-called computation essentially is you get a new matrix. You sum up, you get this matrix. And this matrix were time, you get essentially is you get a original one, every prestige is 1 or something. Then when you do the computation, you have more nodes point to this. You actually add them up. This is a typical matrix computation. You get a row and a column. You're basically doing this computation. Yes. Actually, I know what you mean. Actually, the real computation, actually every time you do it, you actually divide it by the total number of edges. It's not like you keep just adding 1. We were getting into this. We probably get into the detailed formula. Okay, then you will see the computation. Actually, you will normalize it. That's why it can get stable. Okay, that's a good question. Okay, now let's get into the detail. This is just an idea on the one. But the detailed computation, you do need to consider the normalization. And you can see this one is out degree. You get in degree, you get out degree. This one, actually, when you do it, you will divide by the number of out degrees. You will get a normalized adjacency matrix in the computation. Okay. So let's discuss that's a general idea on compute the eigenvectors. Okay. Now we get into the real page rank. The real page rank actually consider more factors. Okay. One factor called random surfing. That simply says, of course, the web is a graph, it's already static linked. Okay, you can do the computation. But when the people are doing surfing, there are many cases when you try to, you are not always follow the links. When you try to reach something, sometimes you need to take a random jump to somewhere. That means if you think of web server, the real traversing is you randomly may choose one of the outlinks from the current page, and you can do jump. Okay. This jump is you can jump to any other page in the web graph. That means you can follow the outlink, everything like suppose you get 10 outlinks. You can say everybody are going out using pure random walk. Everyone I follow this path is 1/10. You get 10% probability to go down there. But in the real traversing, you assume this node also will be able to jump to any other node in the graph. So there's a random factor. Okay. So when you do the calculation, you need to think about both. One is you follow the link, you get a random walk. Another is random surfing. You randomly jump to any other page in the graph. Okay. Of course, this probability is smaller. Okay. You do have a small probability. Then when you calculate the prestige, you need to think about both. One is you follow these out links. If your out degree is d sub out, so the probability you follow the pointer go is 1/d out. Right, d sub out. Because you have 10 outgoing pages, so every one you go is 1/the out one. Okay. Then this is just following the out one. You will go like you will normalize by a number of out pages. When you do the computation, you use this formula. Okay. This is normalized adjacency matrix of the graph. But on the other hand, you do allow random surfing, random jump. The random jump simply says you have a probability. You can randomly jump anywhere. So then when you do the calculation, you are going to think about the probability to jump to any other nodes. You get an adjacency matrix actually is changed. Originally, this one is just the given graph. But this A sub R is, you assume the whole thing is connected. Okay, everywhere you can jump. Okay, in that sense, you get A sub R, this matrix, you have a probability P. Okay, but remember, these two probabilities are not equal. The majority probability actually goes, to the major node. There's a minor probability goes by random jump. So to that extent, you need to calculate both. Since you need to calculate both, you can see is this one is you follow the normal, outgoing edge. So this n to the power t is you follow the normal one. This alpha is the small probability you follow the random surfer. Okay, so that's one. This alpha times this random surfer, jumping to any node in the graph, that's another probability. So the page rank, the calculation actually is a composition of these two. Okay. Of course, if this alpha is bigger, then this part will be smaller. So their total probability adding together is 1. Okay. But this alpha usually is pretty small. then the majority they follow the degrade the outgoing edge they traverse. That's the reason the page score computation is based on this one. Okay. That's their 1998 PageRank paper. Okay. Of course, they did experiments. They use a real graph. They do the experiments to see whether this computation will be able to automatically detect the highly ranked pages. And they found it's very successful. Okay. With a limited graph, with web as a big graph, of course, they took a portion. They found that if you follow this, you'll get a pretty good, prestige rank for the real objects. Okay. Of course, after so many years, the Google at that time was 1998. After so many years, the web graph actually changed quite a lot. This was the old story. The story was that time everybody systematically build links to the others. Okay, like me, I build links for the other famous researchers. I want the students or myself go to his or her web page easily. That's why I myself actually get there, using Gopher or some other things. I found this like Stanford, like Wisconsin, or some famous researcher. I explicitly linked them. Okay, that's the reason this web following the graph, it does work. But now things have changed. I do not link to them anymore. Right? You think about this. I use Google. I do not link them anymore. That actually gives Google a little hard time if you follow the exact page rank to do the computation, because originally the web linked in a very good purpose. You can compute it. But now, since the Google comes, they use PageRank. Actually, they may destroy some base of the PageRank because you don't link anymore. You just say, I Google it. So the real link now is much more complicated. Okay, that means after Google, of course, research-wise, there are thousands of papers following this. But actually, the web graph, since 1998 to now, it changes a lot. Okay. People, if you just base on those links, it may not work anymore. Okay. So, but exactly how they do it, of course, they may not want to publish everything they did. Okay. But they base on this, and they're still moving on. They still use web as a big graph. They still use PageRank. But how important this PageRank, how exactly the computation formula, I should say it has changed quite a lot. Okay. But if you really want to trace Google things, you probably can trace it. There are many things they may not publish, okay, because they want to keep their secret. So Yahoo or Microsoft, they probably cannot duplicate their success that so easily. Okay. But they start with this. Okay. Now you probably can see the PageRank Brian page in 1998. What they did, their general intuition is links like link citations in the literature. Okay, the web link is somewhat similar to this. The page is cited often, usually is more useful in general, then you will give more prestige to this page. So the PageRank essentially is citation counting, if you think about this. But it's not simple counting. It's using this iteration eigenvector computation. You think not everybody's norm is the same, is equal. Remember, nowadays, PageRank, people calculate like H-index or citation index. They still calculate that each link is equal. You cite this paper, I cite this paper, or some very famous people cite this paper. They are equal. Okay. But some people who are not buy it, I actually, this year, I accepted one student who is applying for PhD. He developed another index, which is different from H-index. He did count who cited, okay, and whether this person is famous using some kind of formula similar to this kind of PageRank. That means they will see whether this guy is cited high. If cited high, you cite this paper get even higher one. Then they calculate which researcher is more prestige. Okay, you can see You know, the idea is not that simple, not that complicated, but it's very nice. Actually, people really like his work. His work also published. As a bachelor student, you know, he somehow simulated this PageRank doing the real citation counting, okay, and calculate the new index for researchers. PageRank, since you use a random surfing model, you can see, you say there is a alpha probability random jumping. There's 1 minus alpha probability is just to pick up the existing link, randomly pick up the existing link. The other one is jumping anywhere. Okay, so that's a difference. That's a PageRank algorithm. Almost the same time, there's another very famous algorithm proposed by John Kleinberg, who now is a professor in Cornell University. At that time, he was a postdoc. I think he got a PhD in Berkeley, did a postdoc at IBM. That's why this second algorithm, almost the same time discovered as PageRank, was done by, they call Berkeley and IBM. Okay, so because he actually linked to both groups somehow. That algorithm called HITS, or some people call hubs and the authority. Okay. That one is different from PageRank, but it's also very real. They consider the web in the real case. Okay. Why they consider you need to identify authority and hubs is not everybody would like to link to everybody, even they are very famous. Okay. Just think about this. Okay. Suppose you go to a car dealer. Okay. You go to, suppose you want to buy a car, you go to Toyota. You say, I want to buy, BMW. Okay. So what Toyota people will say? The Toyota people say, oh, our car is far better than BMW or something. But if you say, if you really want to buy BMW, go to the other dealer, don't come to me, right? Actually, that's a competition. In a sense, you think about it, you go to the website. Of course, you go to real dealer, they may say that. Going to website, you go to Toyota website, you will not find a single trace of BMW, right? They don't point to it because they just pretend that they never exist, only Toyota exists, right? So all the rivals gone. That means even Toyota, for the car page, Toyota is one of the popular one. But there are many other rivals. They don't point to at all. They just show in the whole world I'm the only one, right? So that's actually on the web, because it's different from the site, from the research, because any research paper, other people review it. Okay. You actually have to say related work. You will say, all the other people, they did good work on this. I did a little incremental, but I'm better than this. You actually have to cite your rivals and comment which party you are stronger than your rivals. If you don't cite your rivals, you don't assume they exist, you will never pass a review. Okay? Because many reviewers are your rivals, right? They read it, they see whether your claim is right or wrong. So that's different from academic research versus the real web. Okay? Actually, John Kleinberg catches this point. He just say, you think about all the others will cite, they won't. But there are somebody who cites everyone. You think about this. Suppose you go to a used car dealer or you go to a car shop. They actually say, I can repair, or I will sell Toyota, BMW, Honda, all the cars. They list all the brands. Okay. They point to all the dealers. So that's the one they call hub. A hub is kind of service. Service means you want to repair a car, you want to sell a car, you want to sell some used car or something. You point to everyone. On the other hand, everyone will point to you because you serve somehow, help them as well. For example, you sell a used car of Toyota, Toyota may point to you. Say, if you want to buy used cars, go there. Okay. So that's the case. The web, in the reality, there are two kinds of important pages. One is hub, one is authority. The Toyota dealer, the Toyota seller is authority. But the dealer who sells all the cars is a hub. okay, because it's everybody. You point to everyone, everyone point to you. Okay. So to that extent, they actually work out this one. They call the hits has two scores. One called authority score, one called hub score. Okay. And then they have the computation. Let me see. I did not draw some picture. I should draw it. But anyway, what you can see is A is authority, H is hub. Okay. So how you get authority is authority, you type this hub, give you, the hub give you some score. You type this score, you look at this matrix, you get authority score. But how to get a hub score higher, or how to calculate the hub score? The hub score actually is you take the authority one, see the authority point to you, then that's hub score. So the real computation becomes these two things mutually enhance each other. Okay. That means in this formula, these two formulas, you actually can see the H will help A will help H. If you do a little, replacement, you probably can see when you write down this vector form. This authority at the kth iteration, you get a hub's k minus 1 iteration score. Times this matrix, this transpose matrix, you get A's kth iteration score. But this hub score, you actually can replace this hub score by this authority again. You can see this H to sub k minus 1 can be replaced by A, times this A, k minus 2, right? This is just based on this formula. Once you replace this, you can see this computation, the kth iteration, actually is A transpose times A. That means you just have adjacency matrix, but when you do the computation, you actually take A transpose times A as one unit, then you can jump from k minus 2 to k. Okay. For the same reason, if you want to compute the hub score, you can calculate this one is A times A transpose. Then you times H, your hub score is k minus 2 1. Okay. So what does this mean? Okay. This actually, if we go back to the previous one, you remember these two formulas. So A transpose times A. This A times A transpose. Then you go back to our previous one. I think we got this co-citation and a bibliographic coupling. We just did this last lecture. You can see the co-citation matrix is A times A transpose. And the bibliographic coupling matrix is A transpose times A. Now you probably see John Kleinberg actually calculate this hub and authority. The real computation actually use both matrices, right? You can see one is A times A transpose, the other is A transpose times A. One is co-citation matrix, one is bibliographic coupling matrix. That's why actually this hits one, if you look at the hits formula, they actually get both. They get A transpose times A and A times A transpose. That means once they use co-citation matrix, the other one they use bibliographic coupling matrix. Actually, both of them will be useful in this formula. Okay. So this formula, this hits, the only difference between hits and PageRank is also on the initialization. Okay. The hits actually is computed at the query time. That means hits is query based. That means you get this matrix, you do the real computation. When you submit the query, you do the computation. But a PageRank is pre-computed. Okay, because you take the whole matrix without considering any query, you just pre-compute it. Okay. to that extent, even nowadays, if you think about it, the web is so big. The page rank, you do the pre-computation, the query time, it could be quicker. Okay. When you do the query computation, you may involve some non-trivial computation. It could be a little slower. Okay. To that extent, that's also Google, even they look at its algorithm, when they set up, they still use their own page rank. Okay. So you probably can see that. But hits is still useful in many other scenarios. But for search engine, for the big search engine, no matter Yahoo or Microsoft or some other search engines, they essentially using something very close to PageRank. It's not exactly hits, okay, because hits is more query-based. Okay. For smaller graphs, it works fine, or it's efficient. But web scale is really big. Then you want to be really fast. Okay. So that's the hits algorithm, but it's a very interesting one. You probably can see we do a little summary. This John Klein 1998 paper. That paper is together with hits, together with PageRank. These two, in the websites, in the search engine wise, these two are the most two classical papers, and it's cited very, very frequently. You can Google it, see how frequent they are cited, but they are very, influential algorithms. The idea of hits actually is you need to compute both authorities and the hubs. Then you do iterative reinforcement. You can get both computed. But one, like A times A transpose is co-citation matrix. A transpose times A is bibliographic coupling matrix. So then you can see both will be useful. Okay. These, yes? Can you speak a little louder? Bibliographic coupling matrix means the two papers co-cited a bunch of other papers. So that measure, compute that measure, is bibliographic coupling. Bibliographic coupling simply says you get several papers, they cite the same set of paper, they themselves could be rather similar. Okay. They try to see whether the paper, the co-citation matrix is just reverse. You just see, just see what, it's not like citing a bunch of paper. You just say who cited you. That's a co-citation. Yes. Yeah, that's a very good question. Actually, you say the question is whether there are better hubs cited by other hubs. Okay. Actually, this computation, if you see this, because this computation somehow can cover the citation as well, because you actually can see this is the A transpose A. They actually doing those computation as well. Okay. So to some extent, what computed by, if you think authority and hub, these two are sort of like almost identical. Like authority can cite authority, hub can cite hub. Actually, this kind of computation will embed those heuristic inside as well. Okay. So, but just to say the reality, you have these two. If you use this computation, it will be somehow capture that signal better. Okay. But it does capture the other self-citations and citation on the, like a hub can cite a hub and authority can cite an authority as well, because it's kind of iterative algorithm to compute. Both of them are computing the eigenvectors. Okay. Yeah. Of course, after these two studies, there are many, many follow-up studies, and I should say there are thousands of papers on this, not only in WWW, those conferences, but also in many other conferences. You go to data mining conference, database conferences, or machine learning conference, you'll see lots of papers following those algorithms. And they study, for example, some study more refined citation. Just give you a simple example. I got one PhD student, Deng Cai. before he joined me, he already published a very good paper. The paper actually is doing this page rank, but a little refined. The refinement is pretty smart, because he was thinking about one page. You actually can partition into many different parts. Some, for example, is ads. Some could be like categories. And the other citation in the right place, you cite the other one. That's a real citation. You cite, like a different category, like when you share things. Some are the other ads put on the site. Okay? And some actually is a category. For example, you share, say, some bird food. And here on the top, they may have different animals. They have birds, different kinds of birds. You can buy birds. You can buy animals or something. They have many other things, but it's not exactly on their bird food. Okay, so then you have other places that even sell football tickets or clothing or something. So that's a different parts. If you partition them, you compute them separately, you probably get a better idea on who cited who and which one is a real prestige. Okay, so he actually, when he worked at Microsoft Research Asia, he worked with them. He did a lot of study on this. He partitioned this one further. Okay. That's an interesting paper. It's on the multimedia. You partition them, then you do the refined page rank. Okay. There are many such studies, I should say. Then another thing I should mention is there are many other measures. Okay, but as we know, the eigenvector, eigenvalue, these kind of centrality calculation is very critical. But if you look at the others, I do not want to lecture on each one. I just say you look at how many. I just put the measure in the network measure. I just Google it on the wiki. The wiki actually give you see this is start from B, then you get into C, then you get into D. There are lots of them, okay, lots of measures. For example, the very interesting one is the flow. You look at the information flow, information passing, right? Then you have different bridges, prestige, you have radiation degree, you have structural cohesion, you have structural equivalence. There are many measures. So the measure in the web is a big, big topic. The centrality measure or some kind of measure, it has been there for many interesting studies. But we are not going to discuss all of them. I just show the most important one, actually, the eigenvector, eigenvalue one. Okay. This one is a conference. Actually, it's also a web-related conference right in Athens. Actually, I took it from just going out the conference site. You can see that's closer to their Greece, Athens downtown. Those are the 1,000 years ago, the palace. Now it's only a portion left. Now we give you some centrality measure, which is very interesting. Now I give you another topic, is network modeling. Okay. That means you look at the centrality, you think the PageRank is very interesting. But people want to study the whole network to see how this network was generated, okay, either by human or by machine or randomly or in some hidden model they generated. Okay. At the very beginning, okay, mathematicians actually proposed a very popular model called random network model. Okay. The random network model means you get a graph. Okay. What's the next edge was generated? They just assume you're throwing a dice. Throwing a dice, you get this number, you go out to this edge. Okay. The chance to get another new edge is purely random. Okay. They call this network model as random graphs or random networks. Actually, in 1960s, this random graph model was very popular. People, especially in physics and in mathematics, they studied this quite a lot. Okay. But later, people found the real network is far from random. It's not random at all. Even you do not know how the network is formed. But if you really watch this network, you use random network model to compute it, it's very wrong. Okay. So in 1980s, 1990s, when the internet started exploding, people re-examined network, proposed some very good model to model the real network. That means if I mathematically model it, I will generate this one. It's very similar to, say, internet or to some kind of graphs. Okay, they actually later people study many, many graphs. They found network, the real world network, is not random at all. Okay, so that's the reason we want to study network modeling. That means how the network is modeled mathematically. Okay. So what kind of network? We can give you examples. One you can think is communication networks, like internet. You can think internet or those switch, the telephone switch in the early days when there were not so many wireless. You based on very complicated wires, this communication networks. Then there are information networks, like a web. You can think it's information networks. Okay, the link to some extent is virtual link, right? You put a link; it's not a real wire, physical links. There are social networks, like there are so many, right? The Facebook, LinkedIn, so many social networks. Biological networks, people actually found the protein, they link together, they get they get lots of different pathways. They're very complicated biological networks. They want to study those networks, see what are the mathematical models underneath. Okay. So they found the typical real-world network has several interesting properties which actually the random network may not have. Okay. One is actually few connected components. Connected components means they connect together. Okay. Then if there's no one connected to anybody in this component, you get isolated nodes or another component. But people actually found in the real network, almost everything is connected. You try to complete partition them into several, isolated network is very hard. That means you get only one or very small number of connected components. So that's the first thing. Another thing is people found is small diameter. Small diameter means if you want to traverse from one node to any other node in the network, the minimum traversing distance is very small. Of course, you can traverse very far and go there. But the minimum traversing distance is only like 6 or 7. So that's why there are some people who got like 6 degrees of separation, the network model. Actually, this is pretty rare. Okay. Another one is high degree of clustering. You consider random network, if you count the number of nodes and number of edges, it's very sparse. But in the real network, sometimes some part could be very much clustered. Okay. People actually, I remember people give in one conference, people give some consensus before the network science was become popular. They just say, you think about your friend, okay? On a typical, say, social network or kind of a friendship network, what is the average degree? Okay, what is the average number of friends on this very big network? Like you get billions of nodes in Facebook. What is the average degree? Okay, a lot of people say 100, okay, or 50, or 200, or something. Actually, people finally found this average degree is very small. Okay. But what is maximum degree? Actually, it will be really, really big. The maximum degree could be 100,000 if you think about this. That means it's not even. Okay, so this is one. Another one called heavy tail distribution. Heavy tail distribution means there are a small number of nodes. Their degree is really, really high. Okay, but the majority actually is pretty low. So they get this tail. You have a head is very, very high. but you have a very, very long tail. Once you stretch it down, it will become really, really small. Okay. Actually, some people study the research publications or citations. They found the same thing. Okay. Some paper, you get a very small number of papers cited so popular, hundreds, thousands, or tens of thousands times. But majority paper only cited once or twice. Or some people write a paper, no one cited. Okay, so you will find it's a long tail. You get a very, very large number of papers, nobody cares. Okay, so that's the citation is also following the power law. Is heavy tail. Let's look at a little more serious. We look at the real network. Okay, the real network usually is very large, very sparse. Large means you get the n, the number of nodes and number of edges is really big. Sparse means the number of edges versus the possible edges is very small. Okay. Possible, you think about it, you get billions of nodes. The possible edges, the number of possible connections is just too big. Anyone can connect to anyone, but it actually only connect a very small number. So that's why it's very sparse. Okay. The small world property, usually they represent this formula. Okay. This is the path length, okay, and this is the number of nodes in the graph. The small world means if you want to traverse to any other nodes, okay, this length, the traversing distance you reach to the other one is in the case of a log n. Okay. Log n simply says is exponential. Logarithmic is smaller, or you can say exponentially bigger. You can connect them. So this is a small word. Actually, there are even people call these as ultra small word. Ultra small word means this one is much less than log n. Some people put a double log there. It's a log n. Okay. So it simply says the real world, like you think about the web, is so big. If it's you only have 6 degrees of separation, it's really log. You can put 2 or 3 logs there, right? So it's ultra small word because it's so powerfully connected. Then the power law distribution, simply some people call a scale-free network. What do you mean scale-free? Scale-free, you probably, if you do the complexity analysis, you say, my algorithm is linearly scaled is much better than the other one is quadratically scaled. Linear scale means if you added 10 times more things or data into your algorithm perform probably expected like just 10 times slower. Okay, so that's a linear scale. The quadratic one means you get a 10 times you add it into the data size, you probably the algorithm will run 100 times slower. Okay, so that's quadratic. But the scale free simply says you do something almost like a logarithmically, or you add things in, you almost do not see they really change in that big. You think about your small world. Even you add more nodes in or add more edge in, you still have something like 6 degrees of separation. This is really scale free. Okay, that means you add 1 billion nodes, you still get that number. That's almost do not really impact their minimum length, right? Minimum distance. So that's why they call this is a scale-free network. Okay. And the scale-free network, if you write down like the probability, they usually write down like this. You can see this is the power law because this is the k to the power of minus gamma. Okay. Then one interesting thing, if you see whether your data follow the power law or not, very interesting one is if you take a log on your function, you just think about this one is your probability. If you take a log, what you will get? Okay. If you take a log on this one, this f of k, then you take a log on this, you can see you get a minus gamma log k plus log alpha. What does this mean? This means if you think of this k is x, your function is y. This log y and log x actually is linear. That means if you take the scale, if you think about it, x is your one axis, y is another axis, you take both axes in the log scale, you actually get a line, right? You think about this. This formula basically say, if you take x-axis and y-axis both in the log scale, you will derive a line, a linear line. This minus means the line is this way, right? The plus is this way, right? So I actually can show you this graph. Better show you the graph, you probably get convinced. Let me go down a little to show you the graph. You can see this one. This actually is very interesting. It's very typical one. You want to check a log. See, you take a log on x-axis. That means that you take exponential. It's 1, 10, 100, 1,000 in this scale. Okay. This y is also in the log scale. It's 1, 10, 100, 1,000. Okay. This is power. Okay. This is the power. Then this distribution, you find a line. Okay. That's exactly, if you want to check which distribution is power law distribution, you don't have to draw this, because this is sometimes everything is a curve. You cannot distinguish it. But if you take the log, you draw a straight line. That's very good indication this is following power law distribution, right? Because power law, you take a log, you get line. You get both sides of log. So that's a typical way people prove this network is power law, because they just take a log on both sides. Okay. So then we finish this slide. Okay, I think we probably cannot completely finish it. I don't want to. Okay. So we just stop here. You just know if you take a log-log plot, you get a straight line. That's power law distribution. Okay, then we'll continue this one next lecture. Thank you.